Okay, so in today's lecture, we are going to go further with the enantiomers and we'll show a model regarding the enantiomers. So, as we discussed in the last slide, last lecture, that is, in terms of the enantiomers, they have some key aspects. So, let's revise what those key aspects are and then we'll take it up from there. Okay, so what are these key aspects? So, enantiomers have nearly identical chemical properties but differ in a characteristic physical properties. Okay, so what do I mean by that? So when I say they have nearly identical chemical properties, so they are, that is because they are, the arrangement of the groups in the 3D space are same. So in this case, for example, these two are enantiomers which are generated by mirror images of each other. So this is, you can see this carbon has four different valencies, B, A, X, Y, and this carbon is generated from its mirror image, again A, B, X, Y. So you can see the A and B angle is relatively same to each other. In this, A and B angle are relatively same to each other. A and X are relatively same in each other in both the molecules. Okay, so this is A and X. And this is, let's say, that was A and Y. So this here it is A and X, which is relatively same to each other. A and Y relatively same to each other. So they are similarly, you can say it for B and X. B and X, their angles are spaced equal to each other in both cases. So they have, because the relative arrangement is the same, they have identical chemical properties. But what is different for them is that their interaction with the plane polarized light is different, because when they interact with the plane polarized light, they rotate the plane of the plane polarized light in equal but opposite directions. So for example, if this enantiomer rotates in clockwise direction by 60 degree, its enantiomer will rotate it by minus 60 degrees. So let's say if you are visualizing it, this would be the direction of the plane polarized light. In this case, for this molecule, it is going to be in this direction. Okay, so that is minus 60 degree. Okay, so that is a very key difference. So that is to say that compounds without chiral centers or compounds without chirality, they do not rotate the plane of plane polarized light. Okay, so that is a major distinction between achiral and chiral molecules. And this is something that a lot of students get confused. That is, each chiral center, each chiral molecule can have only one set of enantiomers. Okay, so if you, regardless of if you place the mirror in the forward direction, in somewhere in this plane or in this plane, they are going to have only one set of chiral centers. Okay, so that is a very key important aspect. Okay, so one more point that I didn't mention here in this, and I should, that see, I mentioned that they have nearly identical chemical properties. So why does you use the term nearly? Because in case they are reacting chemically with another chiral molecule, with another chiral molecule, they will interact in a different manner. Then in enantiomers will behave non-identically. So why is that so? Because let's just say that let's just give a small cartoonish representation explanation why that is. Let's say this is a chiral molecule A, B, X, and Y. Here is its enantiomer A, B, Y, and X. So you can see I have done a mirror flipping in this plane and I have switched them. So let's just say that it is reacting with an achiral molecule. Achiral molecule means, let's say, methane. C, D, D, and E. Okay, so if I try to place them next to each other, so this is what it's gonna look like. I'm gonna change the ink and I'm gonna show it to you. So this is, let's say I'm placing them here, C, D, D and E. Okay, and here I'm placing them again, C, D, D and E. So you can see that the relative interaction with the A and C is constant for both of them. D is interacting with X, D is interacting with Y, D is interacting with Y, D is interacting with X, E is interacting with B, both cases. So the interactions are identical. Okay, this is, let's say, for a reaction. So this is an achiral molecule for which the interaction is identical. So let's just try it for another chiral molecule now. Okay, so I'll just draw the original enantiomers one more time with a red color, and you can see that this is A, B, X and Y. On this side also I have A, B, Y and X. Okay, now I will try to see if they will react with another a chiral molecule similarly or differently. Okay, so let's try that with this molecule. So let's call this CEDG. Okay, so let's bring it this molecule next to this. So C, E, D, G, and let's try with this one, C, E, D and G. Okay, you can see in this case A is reacting with C in both cases, B is close to E in both cases, but here the X is next to D and Y is next to G. But here the Y is next to D and the X is next to G. So they are non-identical now. Okay, so that is this point, that when they interact with other chiral molecules, their interactions are no longer is identical. Okay, the last point that I mentioned here. So before I show the model, I'll just discuss how the achiral molecule differs. So the achiral molecule differs in the perspective that their mirror image, if you generate, they would be superimposable with its own molecule, meaning that this is, for example, is an achiral molecule. Why achiral? Because it has identical valencies here and here, and this is its original molecule. So if you rotate this particular bond, this X and X can be brought here, and this is identical with its mirror image. So this differs with this one, where even if you do any kind of bond rotation or whatsoever, it is not going to be identical with its original one. So this point I will show it with a model, because it is a little difficult to show without a model, that the superimposability. So for this I'm going to use the Avogadro. So here we have two molecules which are mirror images of each other. So these are two chiral molecules. Okay, so you can see this is the chiral carbon. So it is bonded to four different atoms: the phosphorus, nitrogen, hydrogen and oxygen. The other atoms, the hydrogens here, they are not relevant because they are not bonded to the carbon directly. Okay, this is its mirror image: phosphorus, oxygen, hydrogen and nitrogen. So if you put a plane of mirror here, you can see this is reflected exactly equally and opposite to each other, right? So this is, you can see this is an imaginary plane of molecule. So you can see they are mirror images of each other, and what I'm going to show is that if the bond rotation, if I do the bond rotation, even then they are not superimposable with each other. Superimposable means if you put them on top of each other, they will not be identical. So first let me do the bond rotation. Okay, so let me try the bond rotation. Okay, so in the bond rotation, what we have here is following, that this is again, as I was discussing the chiral molecules. So I'm going to select this bond and rotate it. Okay, and I'll try to see if I can make them identical. So I have made the relative arrangements roughly the same. So what I mean by that, the oxygen is pointing towards left side, the phosphorus is pointing towards top. Okay, but you can see that even despite that, the hydrogen and the nitrogen, which are here, the nitrogen is on the back, but in this molecule nitrogen is on the front. The hydrogen is towards you in this molecule, but the hydrogen is on the back. Okay, so that they are not superimposing on each other. So that is what I mean by they are not superimposable mirror images. Okay, so let me try now for achiral molecule. So this is an achiral molecule that I have had it ready. So in this case, why they are achiral? Because if you look at their structure, you can see that their valencies are not their four valencies are not same. No, they are the same. So for this carbon, this has two hydrogens. This carbon, there are two hydrogens, and this is oxygen, which is pointing towards each other, and the nitrogen is on the top. So you can tell that these are mirror images of each other, because if you place a mirror light right here, they will be mirror images of each other, right? The hydrogen on the back, this hydrogen towards you, the oxygen is reflected on each other, and the nitrogen is reflected on each other. So I'll do a bond rotation and I will show that these molecules will look identical in a moment. Sorry for the inconvenience, the software sometimes crashes. Okay, so I will just rotate it towards this side. Okay, and you can see that right now the atoms are almost superimposable to each other. How so? The hydrogen and hydrogen, both of them are pointing towards left side. This oxygen is pointing towards right side, nitrogen's pointing towards the top. Okay, so they are identical to each other, right? So that's why they are superimposable with each other. Okay, so superimposable means in the relative space, the 3D space, they can be they are identical with respect to the atom arrangement. Okay, so that is that. So now let's go back to the lecture. So this is an example. You can look up which ones are the chiral center and which ones are the not. So this is a ribose adenosine. Adenosine in the adenine in terms of the ribose sugar. Okay, so let's try to understand which of the carbons here are chiral or not. Okay, so what you can do here is that point out that carbon 1, you can readily see that is chiral, because that for the carbon 1, which is here, the valencies are not identical. So oxygen, hydrogen, nitrogen and carbon, right? So that is definitely chiral. Okay, I have put star here as a marker of chirality. For carbon 2, a lot of people get confused, because if you look at this valency, it is hydrogen, oxygen, carbon and carbon here. So it looks like on the first glance that it is achiral. So if I'll just write down the valencies in this case, and then I'll highlight why they look like they are not. They're achiral. So the first valence is the C1 on this side, then hydrogen is there, okay, which is this one. Then you have the OH, okay, and then you have the C3. Okay, so looks like they are identical, right? But if you look closely, the carbons extensions For example, here that is nitrogen, carbon 1 extension, and a hydrogen. For C3s, the follow-up valencies are H and OH, meaning they are non-identical. Okay, had they been similar valencies, similar for follow-up valencies on it, then it would have been identical. Then they would have been identical. So meaning that this carbon is also having, C2 is also having non-identical 4 valencies. So this is also chiral. Okay, so this is also chiral. So you can try doing that for the rest of the carbon and see if you can figure it out. The answer is already provided and you can try it out. So this is another example where you can try to see if the following carbons are chirals or not. Next thing I'm going to discuss is diastereomers or diastereoisomers. So diastereoisomers are molecules or stereoisomers when 2 or more stereoisomers of a compound have different configuration of at one or more of the equivalent stereocenters, and they are not mirror images of each other. Okay, so that's the definition, but let's just understand what exactly does it mean. Okay, so I have put up some examples from the sugar chemistry here, and we can have a look. So these two molecules, you can clearly see they are enantiomers of each other, because if you put a mirror image right here, so they are reflected, right? H, NH2, NH2, OH, OH, H, H. So they are enantiomers. Similarly, these two molecules, they are enantiomers because if you put up a mirror here, this would be reflected. Okay, so this fits to the definition we learned that enantiomers are mirror images of each other. How about the relation between this molecule and this molecule, and let's say this molecule and this molecule? So let's number them 1, 2, 3, 4. What is the relation between so 1 and 2 are enantiomers, 3 and 4 are enantiomers. How about the relation between the rest of them? So 1 and 4 are diastereomers. How so? Because if you look at the arrangement of this carbon, this is an achiral carbon, right? So this is an achiral carbon. This carbon's relative arrangement is the same, but this carbon's relative arrangement has changed. Okay, so look up the definition again. So if there are more than one chiral centers, then it is changed in one or more but not all. Okay, so in this case there are 2 chiral centers in this. Okay, 2 chiral centers are present, but only one where it is changed, but the other one is unchanged. So that's why they are diastereomers. Okay, so again let's look up at this example. So I'm saying 2 and 4 are also diastereomers. How so? Because in this 2 and 4, this position is unchanged. Okay, so this position 2 chiral center is unchanged because you can see their relative arrangement is the same, but this position is getting changed. Okay, this position getting changed, so their relative arrangement is flipped, so NH2 to H has reversed. Okay, so they are diastereomers with respect to this chiral center. Okay, let's look at one more example of the diastereomer. So this is from sugar chemistry again. So this particular molecule is D-allose and D-glucose. So can you tell which of the carbon is diastereomers and how so? So if you number them 1, 2, 3, 4, 5 and 6, same for glucose. If you try 1, 2, 3, 4, 5 and 6, 3, 4, 5 and 6, 1, 2, 3, 4, 5 and 6. So you can see that glucose and allose are diastereomers because the following, so there are how many chiral centers are there? There are 4 chiral centers in both of them. Okay, that is C2 to C5. Okay, why they're diastereomers? Because C2 is unchanged. Okay, so this is okay, unchanged. C3 is changed. Okay, C4 is unchanged. C5 is unchanged. Only one carbon out of the 4 chiral carbons, that is C3, has changed out of C2 to C5. So they are diastereomers based on the definition we just learned. D-allose and L-allose, they are mirror images of each other. So why so? So D-allose is this one and L-allose is this one. They are enantiomers of each other because all the chiral carbons stereoisomerism has reversed. So C2, that has flipped, right? So this is on the right side, the OH, this is on the left side. C3 has flipped, left and right. C4 has flipped, left and right. C5 has flipped, left and right. Okay. D-glucose and L-glucose, they are also enantiomers of each other because C2 has flipped between left and right, right? So OH has moved to the left side. C3 has flipped because they have, that is also reversed from left to right. C4 has flipped because it is also moved from right to left. Okay, C5 has flipped left to right. Okay, so they are enantiomers of each other. So D-allose and L-allose are enantiomers of each other, and D-glucose and L-glucose are enantiomers of each other. So I'll explain in a short while what exactly D and L means, but let's just be clear about the diastereomer and the enantiomers. Okay. So diastereomers, to summarize, this stereochemistry is also applicable for optically active molecules, that is chiral molecules. So they have completely different arrangement of atoms in 3D space, meaning enantiomers, the relative arrangement of 3D space is all identical, right? So we have seen that A, B, Y and X. So their relative arrangement, let's say with respect to A to Y, A to X, is identical. But for diastereomers, if you look up these pictures, this is completely changed. Okay, so they have different optical properties with respect to plane polarized light and definitely not equal in the opposite rotation, which we see for the enantiomers. And of course, because the 3D arrangement is different, it interacts differently with other optically active molecules like enzymes. Okay, so that is the definition, that is diastereomers in a nutshell. Okay, so I'll stop this video right here.